Sure. Let's briefly go over what we covered yesterday. Yesterday we covered, yep.
So for that, the plus 6, you don't need to write the 1/3 on the plus the negative charges?
No, because there are more significant contributors. It's not an equal sharing of electrons. And so we can't really put an exact value for how much the negative charge is going to be. Yeah, good question. So yesterday we said the basic rules were we can't break sigma bonds, we can't ever exceed an octet, and we only move lone pairs or pi bonds. And then the last one was we want to show the pushing of electrons by using these arrows. And we always want to start at our electron source and have the tail or the head of the arrow go to the electron destination. And I was really trying to emphasize that when we draw resonance structures, it's not that it's flipping back and forth, it's that the true structure is a hybrid of the two. So we said if you have a blue horse and a red donkey in the brackets, the true idea of the molecule is more of purple mule. So let's get started a little bit on identifying the predominant structures or most important resonance structures. Yesterday, the ones we saw all had equal contribution. The ones we'll see today do not. And let's make a list of rules for assigning priority. Let's rephrase this. Rules for the important of resonance structures. All right, rule number 1 is full octets take priority. And this is something that's a little counterintuitive. And let's take an example of this. I want you guys to draw the Lewis dot structure for carbon monoxide, CO. So there should be a total of 10 electrons in this system. Raise your hand if you think you got the Lewis dot structure already. All right, I'll give you guys a minute more. All right, let's take a look at the Lewis dot structure here. We should have 10 total electrons. So a valid Lewis dot structure could look like this with a triple bond between our carbon and oxygen. What would the formal charge be on our oxygen if I were to draw it this way? +1. So we would put a plus above the oxygen. And what about the carbon? -1. So we'd put a negative there. What do we call it when we have both a positive and negative in the same molecule? Zwitterion, yeah. So let's determine if there's a resonance structure for this. And what I'm going to do is I'm going to move one of these pi bonds over to the oxygen. So what if we have a carbon double bond to the oxygen? Now the carbon's neutral. It's got 1, 2, 3, 4 electrons around it. It has a valence of 4. The oxygen has 6 electrons around it. It has a valence of 6. So we can bracket these in and say these are resonance structures of one another. Which one do you think is a major resonance structure? It's tricky. Rule number 1, the most important rule, is that full octets take preference. Which one? The one on the left or the right has full octets on all the atoms? The triple bond. So if we look at this carbon on the left, has a full octet. This oxygen has a full octet. Versus this carbon over here, it does not have a full octet.
What do you mean by that?
Meaning if we count the electrons around this carbon, we've got 2, 4, 6. We don't have 8 total electrons around it. So if we're assigning priority here, we would list this one as our major contributor, and we would list this one as our minor contributor. Even though carbon monoxide and the major contributor has charges, this is the predominant or most important resonance form because it has a full octet. So if we look at this, it's not quite a double bond, not quite a triple bond, but it more closely resembles a triple bond than a double bond. So it's not perfectly split down the center. Does that make sense? Sometimes it's counterintuitive, but always look for full octets. Rule number 2 is if all atoms have an octet, then the resonance structure with minimized charge takes priority. We saw that on the problem of the day when I asked you guys which one's going to be the major contributor. It was one where it was neutral. If there's an option where you have full octets on everything and there's a neutral version of one of the resonance structures, that's going to take priority. That's going to be your major contributor. All right, third one. And then we'll do an example here too. Third one says, if comparing 2 resonance structures, the one with the negative charge on the most electronegative atom takes priority. And I'm going to abbreviate electronegative as En. And again, this only holds true if the octets are full. If we go up and we look at carbon monoxide, our example, oxygen actually had a positive charge on it, and that was our major form. If the octet rule is being satisfied, but there's a positive charge on an electronegative atom, that's actually okay. That's our trump card. It has to have an octet in order to be considered a major contributor. The last one is avoid drawing molecules or resonance structures with both a carbon that's positive, so I'll write C+, and C- in the same molecule. These are very, very minor contributors. So what I mean by that is, let's take our typical alkene, and I'm just going to choose ethene or ethylene. If we tried to draw the resonance structure for this, we could say, oh, well, why don't we move this pi bond over here? and say that ethylene has this resonance structure where one carbon now has a negative charge and the other one has a positive charge. And we can bracket this in. While we can do this on paper without violating any of the octet rules, this is a super, super minor contributor. So you don't need to draw any molecules where you have a positive and negative carbon in the same molecule. It is okay if you do have two charges, but one of those charges is on a non-carbon atom, like a nitrogen. We saw that with our problem of the day. All right, let's do a practice one and try to put these rules to use. And what I want you guys to do is to come up with 3 different resonance structures, so 2 additional ones, and then assign priority 1 through 3. Yeah, right there. Is it okay if I scroll up? Okay. All right, so for this starting molecule, I'm going to put CH3C. Let's determine 2 additional resonance structures for this molecule. Once you think you've got it, check with your neighbor and see if you can agree with 2 additional resonance structures. I'll give you a hint. One of them violates Rule 4, so it's okay to draw that one in this case. We just want to use it as an example. Let me add in these electrons too. And I'll fill in my sigma bond framework just to speed this up a little bit. All right, so let's take a look at this. What if I move this pi bond up to this oxygen? So now we've got a negative charge on our oxygen. Am I missing anything else? The carbon should have a positive charge, right? We just took its electron, so I'll label this as positive. And then the negative charge should be down here. Does that look like a very significant contributor? No, what rules is it violating? Yeah, we've got a carbon with a positive and negative. And what about rule number 1?
There's no octet for the center carbon.
Exactly. The central carbon does not have an octet. So we can immediately label this one as a very, very minor contributor. Once you guys take organic chemistry for a while, this will just intrinsically look wrong to you. It's just like, ugh. All right, let's continue pushing arrows. What if I move this lone pair over to the carbon-carbon position? Now we've got a carbon-carbon double bond, and then this oxygen still has a negative charge on it.
Yes.
That looks pretty good. All right. So now we've got to pick between the one on the left and the one on the right. Which one's going to be more significant? One on the right, or I heard a left in there. What?
Right.
Right.
Right one.
Why do you guys think the one on the right?
The oxygen.
Exactly. The one on the right has the oxygen with the negative charge. So this one we're going to list it as a major contributor. I should say has the negative charge. Whoop. And then the one on the left is going to be somewhere in the middle. So I'll label this as our minor contributor. So this is what we have to do a lot of times. We identify our major contributors. So if we were to take a snapshot of this molecule, it would most closely resemble the one on the right. It would have some characteristics of the one on the left, meaning that carbon-carbon bond would have some double or single bond character, but it's more closely resembling a double bond. And in reality, the one in the middle, it really wouldn't look like that at all, even though we could draw that. Yep.
So in the hybridized structure, would you put a delta positive on the central carbon?
You could. It's just going to be a very, very, very small delta positive. Yeah, that's a good question. All right, so what I want you guys to do right now is, with the in-class activity, grab that in-class activity, get in a group of 3 to 4 students. You guys can move around the room however you'd like, and start working on these. Try to draw as many resonance structures as possible, and then go through and label them from most important to least important.